In this video, we're going to look at the uniform convergence of continuous functions. And I have a background video called Sequences of Functions, Pointwise and Uniform Convergence. And we noted that if we have a sequence of real numbers that converges, then not many properties carry over from the convergent sequence to the convergent sequence of functions to the function it converges to. So we introduce some new properties. And in here, we're going to show that if the functions meet pointwise and uniform convergence and the sequence of functions are continuous, then what it limits to is also continuous. And so as a reminder of what the definition of continuous is, let's let f be a function defined on a set D, which is a subset of the reals. F is continuous at point x0 or x naught. If given epsilon greater than 0, there exists a delta greater than 0 such that this difference is really small whenever the difference between x and x naught is less than delta, and this is for all x in D. Now we say that you can write this also as that as x approaches x naught, then f of x is equal to f of x naught. So in the theorem here, it says let f be the uniform limit of a sequence of continuous functions f of n, then f is continuous. Okay, and that's what we're going to prove. But to show f is continuous, then we have to show it meets the definition of continuous. So for the proof, let's let x and x naught be in our set D, and then epsilon greater than 0. Now let f of n be continuous functions on D, and this is for all n. And note that since f is the uniform limit, that means there exists an epsilon over 3 greater than 0, such that there exists an n, such that n greater than n, that this condition is met. And this is for all x. This is the definition of uniform limit in our background video. That's true. So now, since f of n is continuous, then we know that there exists an epsilon over 3 greater than 0, or given epsilon over 3 greater than 0, there exists a delta greater than 0, such that when x minus x naught is less than delta, and this is for all x in D, that this difference is really small. It's less than epsilon over 3. So notice that f of n and f of n, and then it's continuous at x naught, for this for all x. Okay. So now let's look at this. The absolute value of f of x naught minus f of x. So this is the part of the definition of continuous that we're going to start dealing with. So here it's equal to this if we add 0. Add, subtract the same thing, add, subtract the same quantity. So this absolute value is the same as this. Now, so now we know by the absolute value inequality that we can look at these separately, and this is bigger than what we started with. Okay. Now this next step, which is crucial, notice that f is the uniform limit of f of n, right? So this gets really small, say less than epsilon over 3. We showed that. Now, f of n is continuous, right? So that means that this gets really small, say less than epsilon over 3. And f is the uniform limit of f of n, and this is for all x in D, which x naught is in D, and all x are in D, that set. So this gets really small, say less than epsilon over 3. Well, this is equal to epsilon. So this is saying that given epsilon, there exists a delta such that this difference is really small whenever x minus x naught is less than delta, and this is for all x and d. So we've just proved that continuous carries over from our limiting sequence to f. Well, that's all I have for today. Hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.